Welcome back to ECE 441A, 541A. Several announcements, obviously, since they're filling the screen. Homework number 6 is due today, and there's a couple of videos and lecture notes that might be helpful in working through that. One is the root locus rule number 6, which discusses departure and arrival angles, departing from poles and arriving at zeros. Those are complex conjugate poles and zeros, is when you apply rule number 6. And there are different pole zero patterns that look geometrically similar, but they may be spaced differently that actually lead to different root locus patterns or diagrams, and that's discussed in another video, which is really dealing with rule number 4. How does the value of the gain k change as you move along a root locus segment on the real axis? Do you experience relative maxes and relative mins, or does it just do a monotonically increasing behavior between, let's say, a pole and where it's going in its destination? There is no class, there is no university being open, or this university is not open on Friday, the 11th. So well, you can show up for class, but I won't be here. Homework number 7 is due a week from today. The exam is a week from Friday. And I thought, since we're not meeting, maybe, and my calendar was open, let's have some special office hours on Monday, which is similar to the Wednesday time frame from 12:30 to 2:30, if you would like to have some opportunity to see me other than the normal classroom. And I may offer some more special office hours leading up to our exam, which is a week from Friday. That's happening rather quickly. We need to get quite a bit of material covered. Exam number 3, again, is next Friday. Lab number 3 is due the last day of class, but lab number 3 is dealing with controllers for our particular mechanical system, and in that sense it might be helpful to look at that because you're implementing a phase lead controller and a PID controller on a particular plant, and that may be possible topics for exam number 3. If you are in 541A, there are the deadlines for the different deliverables. Today what I want to do, last time we covered phase lead controller design, but in that case, we knew exactly where the root locus was after we put down our poles and zeros. In other cases, we might not know quite where the root locus is going, but we may want to assign it to go to a particular point. And we will use then the phase angle condition to try to determine how do we position our pole if we've already assigned the zero. Last time we knew how to position our pole based on the breakaway rule, and we wanted that pole to be to the left of some particular value of S because we knew the particular pattern of our root locus shape. But what you will see then, if we had a no pole zero cancellation, now we might have a 0, or we will have a 0 if we have a phase lead controller in our G sub C G combination, our controller plant combination, which means we no longer have this pure 2-pole system. We now have maybe 2 poles and a 0, maybe 3 poles and a 0. It would be nice to get a little bit of a feel for what that might mean, and that's what I'll talk about very quickly. But really bear in mind that our design specifications, as far as these vertical lines determining our settling time, the angles determining our percent overshoot, the horizontal line determining our peak time, those are really just guidelines, rules of thumb. They aren't exact rules that are going to be precisely held. And our dominant poles, when we have more than just 2 poles in our S-plane, our dominant poles will dominate the response, but they may not be the exact response. So they're just giving us good indications as to what we might expect from our response. Here's what we would expect if we had a pure two-pole system. That's this percent overshoot curve relationship between the damping ratio and the percent overshoot. And it goes down as you increase the damping. The damping ratio is going to vary between 0, which means you have complex poles on the imaginary axis, and then you just ring and ring and ring, all the way to zeta equal 1, where you have purely real poles. And you know then if you wanted a 10% overshoot, you could read over and you now say, oh, I want a damping ratio of 0.6. And that influences your angle. Or if I want a 5% overshoot, now I need a 0.7 value for zeta, and we said that's a nice selection or option if you get complete freedom over the speed of response and the overshoot and the behavior. 5% overshoot's a pretty nice value, or an angle of your two dominant poles of 45 degrees. These are, again, just rules of thumb. If you now start having more poles and more zeros, then you have to just sort of use these as guidelines. It's not going to hold true and fast. And what you can do is you can look at some figures to start to get a feel for what happens if you just had a three-pole system, no zeros, or if you had a two-pole system with a real zero. And these are the figures that indicate that kind of response. It's a little bit difficult in this figure 511 to actually see the green poles that are on this line that has a distance from the origin of 1. So you could think of this as a normalized plot of two complex poles and a third pole that varies as you adjust gamma. And the bigger gamma is, the closer that's going to get to the origin. And the closer this third real pole gets to the imaginary axis relative to these dominant poles, the more influence it will exert over the pure two-pole system. And that's illustrated here in figure 512. If you look at the dashed curve, that's a pure two-pole system with a zeta value of 0.45, which, what's the percent overshoot for a zeta of 0.45? You can actually read it off of this curve, can you not? The final value is 1, and where are you peaking with the dashed response? 1.2, so this is a 20% overshoot, 0.45, and we can go back to figure 5.7 and say, oh, if we wanted a 20, or if we had a 20% overshoot, that puts us at a 0.45 zeta value. Is it clear where that's coming from? Or how you can get that? You can get it two different ways, exactly, or directly off the diagram, or realizing that that 0.9 is actually 2 zeta omega sub n. And what's omega sub n in this transfer function? It's 1. So omega sub n is 1. 0.9 is 2 zeta 1. So zeta is 0.45. How does that change? Well, if you have now a pole, a third pole in this transfer function that's located at minus 4.5, and your dominant poles are a distance of 1 away from the origin, but they have a real part of minus sigma. And sigma is zeta omega sub n. So they have a real part of 0.45. This is now a factor of 10 beyond that in terms of the real pole, the pole being at minus 4.5. And it didn't change the dashed response much, because that third pole is quite fast relative to the two dominant poles. Contrast that with the solid black line, which now has a third pole at 1, s equal minus 1. Now it's much closer to the origin. It's going to influence those two poles because they're all three sort of there playing together. They're all a distance of 1 away from the origin. And you can see then that it actually has reduced the overshoot behavior, and it's maybe even sped it up a little bit because it's now playing together with these two other original dominant poles. So this is trying to give you a feel for how a additional pole might impact your behavior over or contrasted with a pure two-pole system. So obviously with three poles it's a little different, and in the third pole, if that's all you have, it depends on where it is relative to the two dominant poles. If it's closer, then it's going to have more impact. The more interesting behavior, which I apologize maybe if this is color challenged by color, but I'm trying to end, that purple sort of washed out what I was trying to show, but here this ratio of A over zeta omega sub n. Remember what zeta omega sub n is. That's the distance of the real part of your closed loop poles. But A is the location of your zero. And I'm trying to color code. We just have one zero. I've actually shown four there because we have four different colored responses. The pure two-pole system is the green curve. And you can see that it's now has this 20% overshoot. But now if we look at what happens if we put one real zero together with those, it's now the yellow zero at minus 10. It doesn't change much, does it? Because it's quite far away. But as you slide that zero, that real zero, closer to the imaginary axis, now when we get to the light blue, now it's really basically sort of a factor of 4 away from those dominant poles. And look at the overshoot. It's changed. It's almost doubled your percent overshoot. That zero is now giving you some derivative action in addition to your nominal two-pole system behavior. If we go even closer and put that pole to have the same zero real part as the pole's real part, that's what this ratio of 1 indicates. The green pole is right underneath, or I'm sorry, the green zero is right underneath those poles, and look now at your overshoot. You're almost at 100%, not quite. You're at maybe 80% overshoot. And what happens if you put that zero even closer than the real parts of the complex poles, which is this purple color? Now you have an overshoot of over 200%, right? You now have 3.2 minus 1, 2.2, so 220% overshoot because of that zero getting closer to the origin. And what are we doing with our controllers? We're probably putting down a zero on the real line, and that's going to influence our percent overshoot, which means we may want to overcompensate the angle of our poles and say, let's collapse those more than an angle of 45. Maybe we need to get those even closer to the real axis because we know that real zero is going to deteriorate the pure two-pole response behavior. So which angle are we talking about when I'm saying 45? In this case, the angle is not 45 because the angle is such that you have a zeta of 0.45. I have too many 4.5s going around, but an angle of 45 is a zeta of 0.6, and that's the angle that the poles make with the real line. So when I'm saying a sweet spot or a nice value, if we just had a pure two-pole system, then I'm saying it would be ideal to have these complex poles where that angle is our 45 degrees. And now if we introduced a zero in here and it was that location, now we would have something that looks more like this green curve, which now it didn't have a 5% overshoot. It now has a more than that. This is already starting out with a 20%, so you know that you're now going to maybe be at a 20% overshoot when you really wanted a 5%. Pardon? So now we're not changing the angle. We're not influencing the angle. We're keeping the angle at 45, but now by introducing this 0, that now influences, because now we have two terms in the numerator. If you look at what you really have in this expression, you now have an s plus a 0. So you have something that looks like the pure 2-pole plus the derivative of that you're combining because of that s in the numerator. And that combination of two pieces gives you this additional overshoot that you wouldn't have had if it was just a pure 2-pole system. Let's see if we can now design a phase lead controller based on having to use our phase angle condition to manipulate or locate where the pole of our controller is actually going to live. And what do we have when we have a phase lead controller? What's the structure look like for our controller? What did we say last time? What's G sub C of S look like? It's more than just a gain, right? If we just had a gain, G sub C would be K. But a phase lead controller, and here if you wanted maybe 20% of your answer, you could just write down the following. You could say, oh, a phase lead controller is that. But really what you also need to realize is the relative location or distances of those zeros and poles. If I now had something here and something there, which is here and which is there? In this case, we have our 0 closer to the origin than our pole in the complex S-plane for a phase lead controller. And what are the characteristics? Why are we introducing this particular pattern of controller? What are some properties that we can now associate with the introduction of a phase lead controller? One is we may want to actually make our system faster. We may want to speed it up. And in that case, we may want to introduce a phase lead controller. We're trying to maybe pull the dominant branches of our root locus further into the left half plane by introducing this combination of 0 and pole. We may also want to reduce our percent overshoot. Those two together really are going to change our transient behavior. But another property that's really maybe the one that we have to trade off is we may actually sacrifice our steady state accuracy. We may make our steady state error bigger by introducing a phase lead controller. But now we've sped it up, so there's this trade-off that we have to negotiate. This may, introducing a phase lead controller, may increase the steady state error. Let's work through an example and see if we can build a phase lead controller to meet or satisfy our particular design specifications. Suppose we are given a system that has a real 0 at -1, it has a pole at the origin, and it has two more poles, and where are they located? The way that I've factored that is to explicitly identify that we have a real part of -1 and an imaginary part of 1, or j. So we have -1 plus and minus j. We have a pole at the origin. We have a 0 at -1. And we have poles at -1 plus and minus j. That's our pole 0 pattern, and we have a nominal scaling factor of 4 in the numerator, and that will actually influence our gain when we start computing our gain later on. But what's the root locus of this pole 0 pattern look like? We've already done rule number 1 by just putting down the poles and zeros. Which segment of the real line belongs on the root locus? Is there any part of the real line that is on the root locus? That pole is going to migrate towards the 0 at -1. What's the pole 0 excess? We have 3 poles, 1 0. Our pole 0 excess is 2. That tells us now that we have asymptote angles, or let's say the fundamental angle is now 180 divided by 2, or 90 degrees. And where is that? So we now have plus and minus 90. Our branches that go off to infinity of the root locus are going to be going to plus and minus 90 degrees. Where are those asymptotes centered? Where's their centroid? We now have a pole at the origin, so we sum up the poles. We have a pole at -1 plus j. We have another pole at -1 minus j. And now do you see that you really don't have to worry about the imaginary part? Because those are going to cancel each other out. You could have just said, oh, I have 0, -1, -1. Now we subtract the zeros, and we have 1 0 at -1, all divided by the pole 0 excess, which is 2. We now have -1, -1 plus 1, or -1 divided by 2. Our centroid is at -1/2. The green dashed line represents our asymptote, with sigma sub A equal to -90 degrees. Been a late night. So sigma sub A is -1/2, right? It's not degrees. What's degrees? Phi sub A, and it's at plus and minus 90 degrees. Now, what's happening to those asymptotes? Why did we sketch those? What's the root locus look like? Have we finished? Are we done with the root locus? How many branches of the root locus do we have? 3. We have 3 poles, don't we? We have 3 closed loop poles, and we've really only accounted for one of those branches. And it's between the origin and -1. The other 2 branches with large K are going to approach those asymptotes. We know then that for large K, we're going to be zipping off and asymptotically approaching those asymptotes. And we now need to approach those lines, and what's going to happen? Well, this one's going to go up there, and this one's going to go here. Now, how could I find, if I wanted to, it's not critical in this case, but what rule might I use if somebody said, I want to know exactly how I'm leaving, how I'm departing, hint, hint, that pole? So rule number 6 would tell you how to compute the departure angle if you really needed to find it. A lot of times this is the original root locus. You just need to know, oh, that's not going where I want it. I don't need to get that exact with sketching it. With just rule 2, which is finding the real axis segment, and the asymptotes, you basically sketched that root locus. Now, suppose that somebody gives you design specifications and they've consolidated those into simply saying, I want my closed loop poles or a set of closed loop poles at a particular point. Suppose that they say the design specs that I want to accomplish would be that I want my root locus to pass through S sub delta equal to -2 plus and minus J2. And if we put that on the root locus, now we are saying that we want to go there and there with our branches of the compensated root locus. If we just had a gain in our controller, we would achieve what we've sketched with the red curve. Can we get to those triangles with just the gain? No. Isn't that obvious now from the root locus sketch, a very quick root locus? We are not going to go through those triangles. That said, our controller needs to dramatically change or drastically change the root locus, the original root locus. And that means one way to do that is to introduce a phase lead controller. This is now saying that we want to drastically modify the original root locus, or in this case, root locus with pure gain control. Or we now want to change G sub C from just a gain to being K, S plus Z sub C over S plus P sub C. With the intent that what we're trying to accomplish is the following. We are forced to live with what we started with, which is that pattern, but we want to now end up with branches of our root locus going there. So how do we get our branches? We know this one hasn't changed. This is now J, this is -1, this is J2. How are we going to get the root locus to move to the left instead of going to the right to approach those original asymptotes? How do we sort of change the asymptotes? We now said we want this zero pole pattern and it's phase lead, so that says we're trying to put a zero somewhere here and a pole here. Let's just do a thought experiment. What happens if I now put a zero there? And you can't do this. You can't just introduce a zero because that's a derivative controller and we don't want to do a pure derivative controller. But if I did a zero there, what would happen to the root locus? Which parts of the real line are now part of the root locus? Have I changed anything? Now I'm going to have a branch here, am I not? And these are going to do something like this. Do you see that? That's what would happen if I could ideally just introduce a zero factor, but I can't. I have to put that in combination with a pole. But if I put my pole way over here somewhere, then it's going to come here, and these guys are going to go off like this when they collide. That's the thought process that you have mentally. I don't know what's happening, but I'm starting to... I'm not going to touch anything. I'll just assume that you guys can live in the dark if it goes away. Uh-oh. But do you see now the behavior that you're trying to achieve? Let's then, we want to accomplish S delta equal minus 2 plus and minus J2. We have three parameters to select. We have a zero location, we have a pole location, and we have a gain. The zero and pole will change the root locus shape. The gain will get us to the particular value that we want on that root locus shape. Let's just say that to simplify things, let's make a judicious choice of locating our controller 0 at 2. So that now I'm placing a controller 0 right there at minus 2. I know that that's going to help pull the root locus to the left, further into the left half plane. And that's really just one strategy that is suggested in the textbook. This is to locate the 0, locate the controller 0, under the upper dominant pole. Our pole was at minus 2 plus and minus J2. That's where we want our closed loop pole. So the strategy is, why don't we put our controller 0 right underneath that to have a real value of minus 2. What we now want to do is find where do we locate our controller pole. And we are actually going to use the phase angle condition to determine the value for P sub C. What does the phase angle condition do for us? Well, we know that in the closed loop, our closed loop poles are governed by 1 plus G sub C G equaling 0. We know that. Or, if we solve that for G sub C G, that's minus 1, but we can also write minus 1 as 1 at an angle of minus 180 degrees. Which means that this angle of G sub C of S, G of S, in order for a point to be on the root locus, the angle of G sub C G has to be minus 180 degrees. And we're going to use that to our advantage in the following way. Let's start sketching what we have. We now have a pole at the origin. We have a 0 at minus 1. We have another 0 at minus 2. We have open loop poles at minus 1 plus and minus J. And we want our root locus to actually go through or have branches that go through minus 2 plus and minus J2. If we want the root locus to pass through that point, this red triangle, either up in the second quadrant or in the third quadrant, it's going to do it simultaneously. Now what we're trying to do is figure out where is this pole? We know how to calculate all of the angles of the poles and zeros to that triangle. This is just trigonometry. We can compute this angle. And let's call that angle theta p sub 1. That angle, that pole factor, contributes that angle. This pole factor contributes this angle. Let's call that theta p sub 2. And this pole contributes an angle theta sub p sub 0. Our zeros, should I change colors? I don't know if I should or not, but our zeros now have that angle contributed. Let's call this one theta sub z sub 1, and let's call this one theta z sub c, and let's call this angle, which we don't know, but that's the only angle we do not know in this formula, and we can then solve for it. Let's call that theta sub p sub c. Now, where students typically get confused is they want to figure the angle from this triangle to the other triangle, but we're just figuring angles based on our open loop poles and zeros, and the open loop poles and zeros are coming from G sub C and G. The triangles are where we want the branches to end up, meaning this closed loop pole location does not contribute an angle. We really only calculate the angles based on the open loop poles and zeros. And we want those to algebraically sum to minus 180 degrees. If I have zero factors and pole factors in this combination of G sub C and G, how do I add up those angles? In this case, I really have the angles of K, S plus Z sub C over S plus P sub C times 4 over S plus 1 over S plus 1 squared plus 1 squared. And I want to find P sub C such that that collection of angles gives me minus 180 degrees. But how do I find the angle contributed by the S plus Z sub C factor? Or if I look at this algebraically, I'm really taking the angles due to my zeros, since they are in the numerator or they are upstairs, and subtracting the angles due to the poles, and those I need to equal minus 180 degrees. In this particular problem, what's the angle of K? K is positive. What's the angle of a positive number? If you viewed K as a complex number and you sketched it on the S-plane and you said K is 35, you would draw a line from the origin out to 35, and what's the angle between the origin and 35? 0. So the K's not giving us an angle. Neither's that 4. But we do have theta of Z sub 1. We also have the angle of our controller, which we called theta Z sub C. and we're subtracting from that the angle due to the pole at the origin, the angle of the upper complex pole factor, the angle of the lower pole factor, and the angle of our compensator. And all of those we need to sum to minus 180. Is it clear where those angles are coming from? This theta sub z sub 1 is coming from that. Theta sub z sub c is coming from that factor. And we know exactly from geometry or trigonometry how to compute those because we fixed those angles, or they are fixed from our system. What's the angle of theta sub z sub c? What do I have to do if I'm at minus 2 and I now need to rotate to find an angle to get me to minus 2 plus and minus j2? Actually, plus j2. I just have to go through an angle of 90 degrees. Theta sub z sub c is 90 degrees. What is theta sub z sub 1? And now I like to actually deal with angles that are less plus and minus 90 degrees, or acute angles, meaning I might find the angle of theta sub z sub 1 by taking 180 and subtracting this acute angle, because I can calculate that using trigonometry more easily. So that now theta sub z sub 1 is 180 degrees minus an angle that has a tangent, or the inverse tangent. What's my vertical change in going from minus 1 to minus 2 plus j2? I'm now looking up from this 0 at minus 1 through this acute angle. What's the vertical distance I'm changing? It's 2. And what's the horizontal side? 1. So this is now 180 degrees minus the inverse tangent of 2 over 1. And that's the angle contributed by that 0 in our system at s equal minus 1. What about the angle due to the pole at the origin? What's theta sub p sub 0? Now I'm going up 2 and over 2. That's 45, and I'm taking that away from 180. 135. Theta sub p sub 0 is 135 degrees. Do you see that that's also the angle from the pole at minus 1 plus j1? I go up 1 and over 1. So that also is 135 degrees. What about theta sub p sub 2? How much do I have to vertically change to go from minus 1 minus j up to minus 2 plus j2? Vertically, I have to go 3. And what do I change horizontally? 1. So now I have 180 degrees minus the inverse tangent of 3 over 1. And if I compute that, that ends up being 108 degrees. If I computed this theta sub z sub 1, I have 117 degrees. And now do you see how you could use a protractor? You could actually lay your protractor. If you sketch things right, you could quickly just read off those angles from your protractor. If we've done that, now what do we have? We have 90 degrees. That's the angle due to the controller 0, plus 117 degrees minus the angle due to the pole at the origin, the angle due to the upper complex pole, the angle due to the lower complex pole plus the angle of the compensator, which we don't know, but we know that if we want the root locus to pass through minus 2 plus and minus j2, we can hopefully solve for a non-negative value for theta sub p sub c. And if we solve for that, we end up with 9 degrees. So now we have to put that pole far enough into the left half plane such that it looks up at 9 degrees when it looks at the point minus 2 plus j2. Or schematically, what we are doing is we now need this angle to be 9 degrees. This distance is pretty easy to figure out. That's 2. And what we don't know is that distance, x, but we can find it from trigonometry. We know that the tangent of theta p sub c is actually 2 over x. And now we can solve for x. X is now 2 divided by the tangent of theta sub p sub c, or this is 2 divided by the tangent of 9 degrees, which ends up being 12.6. Where do we locate our controller pole then? We locate it 12.6 to the left of minus 2. So that P, or P sub C, is now 2 plus x, or it's now 14.6. We now have 2 of our 3 parts of our controller determined. We now know that G sub C of S, our phase lead controller, is K, S plus 2, that's where we located our controller 0, and our pole is at 14.6. What's left? Now we have to figure out what K is. But K we know how to adjust, right? We crank it up until we get right to that point of minus 2 plus j2 on the root locus, because we fixed that to be on our root locus by the choice of our 0 and pole and of our controller. And now we just have to remember how to compute the gain. What condition do we use to find the gain K? We can find K from the magnitude condition. Which says now that we have the magnitude of K, S plus 2 over S plus 14.6 times 4 S plus 1 over S plus 1 squared plus 1 squared, and we need that to equal 1. Or if we solve that for K, we now have the magnitude of or the distance from the origin to minus 2 plus j2. We have S plus 1 minus j, S plus 1 plus j, S plus 14.6 all over 4, we can't forget that, times the distance from the 0 at minus 1 to that location, the distance from the 0 at minus 2, or we can now evaluate this when S is equal to S delta, which is minus 2 plus j2. But do you see now, if you had dividers and you'd sketched this root locus properly, you could actually measure those distances. You know how to compute the magnitude of a complex number from the origin to minus 2 plus j2. you know how to compute this magnitude. We just plug in minus 2 plus j2 and add 1 and subtract j, and you now have a complex number that you can compute the magnitude of. If you do that, you end up with k equaling about 9, so that our controller is now designed, our phase lead controller is now 9 times the zero factor divided by the pole factor, and that will produce dominant closed loop poles at minus 2 plus and minus j2 by design. And we'll pick up with a different design on Monday.